Have you ever looked up at the night sky on a clear, dark night, far away from the city lights, and wished you could climb right up there, past the twinkling stars, and explore the vast unknown? Feel the pull of the cosmos, beckoning you to discover its secrets? Imagine a ladder, one that stretches from the ground, a colossal structure defying gravity. Past the clouds where the blue fades into black, and into the silent star-studded expanse of space. This isn't just a fantasy, a whimsical dream confined to the pages of science fiction. Scientists are seriously considering it, meticulously planning and calculating the possibilities. They're exploring the materials, the engineering challenges, and the potential benefits of such a monumental undertaking. It's called a space elevator, a concept that could revolutionize space travel as we know it. Instead of blasting off in rockets with their thunderous roar and fiery trails, we could ride up a cable, like taking a lift to the stars. A smooth, continuous journey offering breathtaking views along the way. Rockets are powerful but expensive and risky, consuming vast amounts of fuel and requiring complex infrastructure. The margin for error is slim, and the consequences of failure can be catastrophic. A space elevator would be gentler, quieter, a more sustainable and environmentally friendly way to access space, and much cheaper, drastically reducing the cost of transporting materials and people into orbit. This could open up new possibilities for space exploration, research, and even tourism. Imagine stepping into a pod at the base, a sleek, futuristic capsule ready to embark on an extraordinary voyage. The doors closing, sealing you in for a journey unlike any other. And then rising smoothly as the world shrinks below you, the ground receding into the distance. You'd see your city, a sprawling tapestry of buildings and streets, becoming smaller and smaller. Your country, a vast landscape of mountains, plains, and coastlines stretching out before you. Then the blue and white swirl of Earth, a breathtaking view of our planet in all its glory. Before entering the blackness of space, where stars ignite the darkness. This isn't science fiction, it's a tangible goal within our reach. It's a massive engineering challenge, but humans have always built big things, pushing the boundaries of what's possible. Pyramids, testaments to ancient ingenuity and unwavering determination. Bridges, connecting communities and spanning vast distances. Rockets to the moon, a giant leap for mankind that inspired generations. A space elevator could be our next giant leap, a symbol of our ambition and our unwavering pursuit of knowledge. A bridge to the universe, opening up new frontiers for exploration and discovery. It's a dream we're slowly working to make real, one calculation, one experiment, one innovation at a time. Imagine a structure so tall it pierces the heavens, a direct route to the stars. How would a space elevator work? What are the fundamental principles that could allow us to build such an audacious structure? The idea is simple, at least in concept. It's an elegant solution to a complex problem, accessing space more easily and affordably. It all begins with a super strong cable, something far beyond the capabilities of conventional materials like steel, or, more accurately, a ribbon. A wide, flat structure designed to distribute stress and maximize strength. This ribbon stretches from Earth's surface, ideally near the equator where the planet's rotational forces are strongest. It extends all the way up to geostationary orbit, a crucial altitude for maintaining stability. That's a staggering distance, about 35,000 kilometers above us. It's a testament to the scale of this engineering endeavor. One end is anchored securely to the ground near the equator. This ground station would serve as the primary access point. The other end, far out in space, reaches beyond geostationary orbit, acting as a vital component of the entire structure. Geostationary orbit is key to the elevator's function. It's the altitude where satellites appear to stay fixed above a single point on Earth, matching the planet's rotation. This synchronized movement is what allows the ribbon to always stay taut, preventing it from collapsing. And at the very top, far beyond geostationary orbit, a counterweight is essential. This could be a massive structure, maybe even a captured asteroid or a repurposed space station. Its immense mass keeps the cable stretched tight, providing the necessary tension to counteract Earth's gravity. This tension is constantly balanced by Earth's gravity, pulling the cable downwards. Simultaneously, the outward pull from our planet's spin, the centrifugal force, acts to keep the cable extended. It's a cosmic tug-of-war, a delicate interplay of gravitational and centrifugal forces. These forces are perfectly balanced, creating a state of equilibrium that is crucial for the elevator's stability. This balance creates a stable, permanent pathway from Earth to space, a revolutionary transportation system that could transform our access to the cosmos. The heart of the space elevator, the very thing that makes this ambitious project possible, is its cable. This isn't just any ordinary cable, it's a marvel of engineering, a testament to human ingenuity. It needs to be far stronger than anything we've ever built. The forces acting upon this cable will be immense, a constant tug-of-war between Earth's gravity and the centrifugal force of the rotating planet. Steel or titanium, the workhorses of modern construction, would simply snap under the immense strain. They lack the necessary strength-to-weight ratio to withstand the constant pull and stress. We need something new, a revolutionary material that can defy the limits of conventional engineering. The answer might lie in carbon nanotubes or graphene, materials that exist at the very edge of what's possible. Carbon nanotubes are tiny tubes of carbon atoms arranged in a hexagonal lattice, making them hundreds of times stronger than steel, offering unparalleled tensile strength. And they are incredibly light, reducing the overall mass of the elevator and making the entire concept more feasible. Graphene, on the other hand, is a one-atom-thick sheet of carbon, a two-dimensional marvel, nearly invisible to the naked eye but stronger than diamond, possessing exceptional strength and flexibility. Scientists are racing to make these materials, pushing the boundaries of materials science, in long, flawless strands, a critical step towards realizing the space elevator dream. Construction would likely start in space, taking advantage of the zero-gravity environment, lowering a seed cable to Earth, carefully and precisely deploying the initial tether. Then robotic climbers would reinforce it, slowly but surely adding layers of strength and stability, trip by trip, a meticulous and repetitive process until it's strong enough to support the elevator, a monumental achievement of engineering and perseverance. How do we travel up the ribbon? With robotic climbers. Pods that grip the cable and pull themselves skyward. They'd be powered by sunlight, using solar panels to soak up energy as they ascend. On cloudy days or at launch, ground-based lasers could beam extra power to the climbers. The journey would be smooth and steady, taking several days to reach orbit. No rocket G-forces, just a gentle ride. These climbers could carry satellites, supplies, and even people, making space travel routine and accessible. Building a space elevator is a colossal challenge. The ribbon could wobble or vibrate, so engineers must design systems to keep it stable. Space is full of hazards. Micrometeoroids and space junk could damage the cable, so it must be resilient and monitored. The forces on the ribbon are immense, especially at geostationary orbit, requiring perfect design. The anchor station must be in a safe, stable location, protected from storms and lightning. The cost would be enormous, demanding global cooperation and investment. But the payoff could transform humanity's future in space. The dream of a tower reaching to the heavens, a concept both audacious and inspiring. It began with Konstantin Tsiolkovsky, a truly visionary Russian scientist and pioneer of astronautic theory. Inspired by the Eiffel Tower in 1895, he imagined a colossal structure reaching far into space, topped by a celestial castle situated in geostationary orbit. He realized a normal tower of that magnitude would inevitably collapse under its own immense weight, so he ingeniously proposed lowering a cable all the way down from orbit, held aloft by the constant pull of centrifugal force. Tsiolkovsky's revolutionary idea was truly ahead of its time, but it laid the crucial groundwork for the modern space elevator concept we actively pursue today. Today, the space elevator remains a dream, with the cable material as the biggest hurdle. Scientists are making progress, but manufacturing a flawless ribbon thousands of kilometers long is still out of reach. If we succeed, the impact would be revolutionary, slashing the cost of reaching orbit and making space accessible to all. We could build giant telescopes, solar power stations, and even settlements on the Moon and Mars. The space elevator is more than engineering. It's a symbol of human ambition, a bridge to the cosmos, and a promise for future generations.